Okay, we're on to page 4. Unit 6, forces. Page 3 we did in a prior video. You can find that. And those are examples. Let's see, 1, 2, 3. Now we have examples 4, 5, 6, 7. So let's run through those. We're going to start moving faster on these. For the parts that we covered in the previous video, the new parts we add will go a little slower. So if something seems too quick, go back and watch the previous video. All right, here we have our 20 Newton block. Good. What do we know about the block? Well, we know it's 20 newtons. That's its weight. We can put that in here. Fg is 20 newtons. Fg covered. Let's see, it's being pulled. We know there's an external force. You only know if they tell you. They actually tell you how much. They said 15 Newton external force at an angle of 20 degrees above the horizontal. Well, I don't want to make that too small, and I like to draw roughly to scale. I'm going to make my Fg a little bigger. This will be my Fg now, 20 newtons. And then here's horizontal. It actually doesn't matter which way you go, left or right with this. Most people prefer right, so I'll go right. 15 newtons, not directly to the side, but 20 degrees above. So something maybe like this. F external, 15 newtons. Great. Okay, what else do we know? Well, frictionless. So that's out. We just did the external. We know there's no spring. We have a normal force. Do not just slap 20 newtons in there because it'll be wrong in this case. The normal force is a balancing force. So how do we do this? We go back to the blueprint, page 2, page 1 and 2 actually. How you deal with diagonal force or a force that's not lined up. Well, you want to break it into components. You have a choice here. You could actually figure out the resultant of these, but that's a mess. You need law of cosine. So instead what you can say is this external force is both to the right and up. How much? Well, it's exactly this much to the right. So that's what we call our external force in the x direction. Some people just write Fx, that's fine. And it also is up. How much up? Exactly this much. That's your force external in the y direction. Now, I prefer to draw it over here because, as I said, I like to draw everything off the center of the box. You could draw it over here, but just be careful, you may lose track of it. Since we are replacing the 15 Newton diagonal with its components, I highly recommend you hash out that resultant. You're not going to use that anymore. Yes, it's still there, which is why we're not scribbling it away. We still need to know in our brains, in case anyone asks, the resultant external force is 15 newtons, but we're not actually going to use that to figure out the rest of the diagram. So, what is external in the x? Well, you have in your reference table ax equals a cos theta. This angle is 20 degrees. You also could just do SOHCAHTOA. This is adjacent. This is hypotenuse. There's your 20. Adjacent hypotenuse is cosine. If you use the quick version, your ax equals a cos theta from your reference table, page 6. Now it's f external in the x equals f external, the diagonal, times cosine theta, which is, let's see if I move this down a little bit. Yeah. Nope, that's all we're getting. Fine. F external, cos theta, is 15 newtons times cosine of 20 degrees, which comes out to, I believe it was somewhere around 14 newtons. We're going to round numbers here, so that's fine. 14 newtons. So our F external here in the x direction is 14 newtons. In the y direction, you can do, let's write it up here, F external in the y is F external sine theta, which is 15 newtons times the sine of 20 degrees. It comes out to approximately 5.1 newtons if I remember correctly. So that is now 5.1 newtons. Great. So we have the external covered. If you look, all of our forces are covered except the normal force. Is there a normal force? Yes. What does it do? Balance. So what does it balance? The perpendicular or vertical direction. How does this look right now? We have 20 newtons down. We have 5 newtons up. There's already 5.1 newtons up. Is there a normal force? Absolutely. Is it 20 newtons? No. The combination of the normal and that upward pull will equal the 20 newtons. That's what we mean when we say the normal is a balancing force. So the normal is actually 20 minus that 5.1, 14.9 newtons. Really, you call it 15 newtons if we're going to do 2 sig figs. So there's your normal force. Are there any forces to the left? No! In fact, this entire picture now is done, except for the net force. Vertically, it's all balanced. Horizontally, it is not. There is a 14 Newton force to one direction. We don't know if it's right or left because they never told us. But there's a 14 Newton horizontal force. Now, if you need to find the acceleration, you do F net over m, which is 14 newtons over, we don't know the mass. You can approximate the mass, or go back to basics. Mass is question mark. Fg is 20 newtons. And it's pretty straightforward from here. Your equation is G equals Fg over m from the reference table, which you rearrange to m equals Fg over G, which is 20 over 9.81, which comes out to about 2 kilograms. And so your acceleration will be about 7 meters per second squared. There it is to the side. Good. Little reminders here are good for you. All right, let's keep going. Now we're ready to hustle a bit more. Example 5. Here's a box. Now I know it says beginning from rest, but don't get caught up with that part of it. The question is really about the dragging as it's being dragged. The beginning from rest just basically tells you it's moving in the direction of the force. So it's being dragged, 10 kilograms. Great, we can put that in the box. Now, what do we know about this thing? Oh, it's being dragged with a horizontal force of 50 newtons. Well, most people like to the right, so let's do that. F external is, they put a plus with it, so we call plus 50 newtons. That's done. What else do we know? Well, we know its weight. That's always a pretty straightforward one to do. Fg, here you can do Fg equals mg if you'd like, which is 10 kilograms times your 9.81, which comes out to 98 newtons. All right, good. Do we know anything else? We got Fg. Now, oh, look at this. It's a wood box. Drag. Sounds like a friction word. Along a level wood surface. Is there friction? Sure there is. Which way is it going to be? This way. How much is it? We don't yet know. In fact, you may even want to do this. Sometimes I like to do this. I do just the stem. We know there's friction, but we're not sure how much, so we're not sketching it in there yet. Let's figure it out. Friction equals mu, or mu, Fn, which for wood on wood, if you're dragging, is 0.30 is the coefficient. Normal force, we need it for this. Well, let's go back to our picture. We're doing friction right now. There's no spring. What does the normal have to be? The only thing left is the normal. So the normal is balancing the weight, which means the normal 2 is 98 newtons. So now the normal force is done. Here's 98 newtons. 0.3 times 98, it's almost 30, it's about 29. So decent sized friction force. Friction is about 29 newtons. There it is. So friction now is done. And the only thing left is to think about the net force. The net force comes from the picture in this case. Vertically it balances, so there's nothing. Horizontally, 50 and 29 the other way. If that was plus 50, here's minus 29. Well, the net force is going to go with the bigger force. So you're really doing 50 minus 29. You're getting 21 newtons in the positive direction. We don't actually know if that's right or left, but 21 newtons in the positive. And the acceleration is F net over m, 21 over 10, which is, easy math, 2.1 meters per second squared. And this 2 is in the positive direction. Good. Done. Now these two questions down here, spring questions. Truthfully, the spring questions are usually very simple, so you can get away without a diagram on them. We'll put it anyway. An external force extends a spring. Normally we're talking about that. They're not talking about hanging anything. You can imagine like a spring attached to a wall, and the spring is here. And so here's like the end of the spring. An external force extends the spring. So here's our external force. They told you the spring constant, okay? And they told you the amount that it was extended. So that external force actually is, let's use, why not? Let's use orange. That external force actually is the force on the spring. Now, this course, the Regents course, is a little funny about it. They define it as a force on the spring. Every other course you'll take, they'll talk about the force of the spring. So really what happens is this pulls the spring, and the spring is pulling back this much, same amount, but let's not worry about that. That is the force in the spring. Fs is kx, we have an equation for that. Fs, the k is 200 newtons per meter. The x, that's how much it's stretched, is quarter meter. And so here, you're not even worried about any of these other forces. You're really worried about the spring force. And this will come out to a quarter of 200, which is 50. So the spring force is going to be here, 50 newtons. Now, these questions can get more involved, though in this course it generally does not. Often the question, they don't get into the F-net. So if you're keeping this at a constant velocity while it extends, or if it's sitting still, the F-net is 0. But you'll see that you can generally run the spring problems in a simple format. They really don't get into the details of it in this course, so we won't either right now. Here, 5 kilogram mass is hanging from a vertical spring. Here's the 5 kilograms. And so, it has a weight. That weight is Fg equals mg, which is 5 times 9.81. We did that on page 3, and that comes out to 49 newtons. Now this actually is, as we defined it in the notes, often you have a hanging object. This actually is the force on the spring. So as it's defined in this course, you're done. In other courses, or maybe an advanced course or in college, I talk about the force of the spring, and the force of the spring is actually exactly opposing that 49 newtons, so that's what it'll be. Okay? Pause.